Okay. Hello, everyone, and welcome back to the fourth lesson of the course of Quality Management and Measurement Laboratory. Today, we will continue the discussion on the basics of probability and statistics. And as usual, let me turn off the camera and starting to share my presentation. Okay. Um, in the last lecture, we came to slide 21, okay, where we discussed it. We are always on the block of slide L03 entitled Basics of Probability and Statistics. So in the previous lecture, we came to slide 21, where we discussed the properties of probability mass function. Just a brief recap, because in this last slide we saw that the probability mass function has the set of real number R as a domain and the interval 0, 1 as codomain, since it's define a probability that, as you know, is always between 0 and 1. The second property is that the probability mass function is always greater or equal than 0 for every mass points. And this is quite obvious from the example that we saw during the last lesson. The last but not least property is that the sum of the probability of the mass function, calculated of course in each mass point, is equal to 1. So the sum of the probability mass function calculated in each xj, that means in each mass point, is equal to 1. Okay? So if we come back to our example, we can see from here that it's quite obvious, since the sum of the probability for each mass points is, in this case, when we throw a balanced fair die, we saw that each mass point has a probability of 1/6, and of course, if we sum 1/6 for the first mass point, 1/6 for the second mass point, and so on to the sixth mass point, we can see that the sum 1/6 plus 1/6 plus 1/6 plus 1/6 has to be 1. And this is what is written down here in the last property of the probability mass function. Okay, so we can go on from this point. But what if the random variable, which, let me remind you, is a function that associates events in the sample space with an x value, a lowercase x value, on the axis of real numbers R? Okay, just the recap. I come back to slide 12. This is the definition of random variable. So it's a variable that associates to the event inside the sample of the sample S, associate a value on the set of real number. Okay, that's the definition of random variable. And in the previous lesson, we saw different examples on discrete random variables, so variable that can assume only predefined value. Okay, for instance, if we roll a die, we can obtain only 6 possible value that are the side of the die. So 1, 2, 3, 4, 5, 6. And what about if we consider a continuous variable? What does it mean? So a continuous random variable is a variable that can take any value in the set R, where on the other end, as already mentioned, a discrete random variable associates only certain values in the set R. Okay, that's the point. So when we are dealing with a continuous variable, the things change. We can make an example of continuous random variable. A continuous random variable, for instance, can be the measurement of a mechanical component in a production process. We know that this measurement can take all values within a certain range, which, as we see during the course, is called tolerance interval. And so not just discrete values. Thus, the concept of a probability mass function, as defined last time, changes because we are no longer dealing with discrete mass points. And with continuous random variable, we introduce the concept of probability density function, also called PDF, which, as shown in slide 22, is related to the cumulative distribution function by using the integral from minus infinity to the value of x, which we are considering, of the probability density function, so fx, of the random variable that in case is called u of du. So we are considering a different function respect to the probability mass function that is reported here. So this is the probability mass function that is the probability for discrete random variable. Okay. While now we are assuming a continuous random variable in which the cumulative distribution function, so the CDF, is defined as reported in the slide. So let's try to do a scheme. I think you can see the whiteboard. So we can see that if x, uppercase x, so our random variable, is continuous, we have that the CDF, cumulative distribution function, that is equal to, I remember, fx of x, is equal to the integral between minus infinity to x of fx of u du. Because why not x and u? Because we are considering theoretical value, but it doesn't matter. You can also write x of the x, okay? And in this case, this function is called is called probability density function PDF. Last time, on the other hand, we saw that for x is discrete, okay, we know that the cumulative distribution function CEF, that is always fx, so uppercase x of lowercase x, fx of x, is equal to what? Well, we saw that by the theory, it's equal to the probability that uppercase x is lower or at least equal to lowercase x. But we we also saw in the previous lecture that this can be write as follow. So we can consider the, we can consider that we are considering the sum of what? Of fx of xj, where that what does it mean xj? Xj are the mass points of our discrete distribution, okay? So in this case, the fx of x, so lowercase fx, is what? Is the probability mass function. So we have two different cases. We have, of course, always the cumulative distribution function, f uppercase f of x of x. But for the discrete distribution is equal to the sum for each mass points of the probability mass function. While for the continuous random variable is equal to the integral between minus infinity to x of what? Of the probability density, sorry, there is a mistake, density function. Okay? And that's the important difference between the two possible situations. So if we are dealing with continuous random variable or discrete random variable. Let's come back to the presentation. Okay, here we have the properties of the new function that we have just introduced. So because the probability density function, as look into the first property, as the probability mass function, so the function related to the discrete distribution random variable, has a domain that is the set of real number R, while the codomain is the set of positive real number R plus. Okay? So before we have that in the case of discrete random variable, the codomain was 0, 1. Now is the set of positive real number. Okay? The second property, again, is is as in the case of discrete random variables. So we have that the probability density function is always greater or at least equal than 0 for every x, okay? The third property said again is something similar that we have already seen in the case of discrete random variables. This is the corresponding properties for the probability mass function. Say that the integral of the probability density function, of course, on all the domains, so between minus infinity to plus infinity, is equal to 1. This is because in this case, and we will see later in the next slide, in this case, the area under the curve identifies the probability. So as the sum of all probabilities of all the mass points in the discrete random variables is equal to 1, this is the same concept. So in the case of continuous random variable, the integral, the area under the curve defined by the probability density function has to be 1. So if the discrete random variable defines the probability as mass points, the continuous random variables define probability as intervals. The last property says that the probability of an interval, so let's consider the interval AB, can be calculated as the cumulative distribution function in B, so the CDF in B, minus the cumulative distribution function in A. So that following the definition of probability density function is equal to the integral between A and B of what? Of the probability density function, so fx of x. But let's see some example with the geometrical interpretation, because of course it is easier to understand graphically the concept. Because as you can see from the slide, in the continuous random variables, as already mentioned, the probability is defined as the area under the curve defined by the probability density function itself. So if we want to calculate the probability between, let's see, A on the left and B on the right, we can calculate the area under the curve between A and B. That means what? What we have already seen in the previous slide. That means the integral between A and B of the probability density function. Okay? That's quite intuitive, because we have a continuous distribution, so we have to calculate the area under the curve or under the distribution to get the probability. Okay? This is a classic example of continuous random variable. In slide 25, we have another example with, of course, a smaller interval in which we have x and x plus h. The interval is smaller, but the concept is always the same. So if we want to calculate the probability that the random variable uppercase x is between x plus h and x, we have to calculate the integral, so the area under the curve between x plus h and x, okay? It's quite, I think that it's quite intuitive. But now we have we can have some doubts about that distribution, because the point is, what's the shape of the density distribution that we saw in the previous slide? What's the shape of this distribution? Well, it depends on the case study. For instance, in this slide, we have an example in which I don't want to go into details because we will see also in the future lesson this concept. So I don't want that you understand at this point the concept of exponential distribution, but I want that you understand the general concept about probability density function. So let's consider this example with an exponential function that is a function widely used to describe the reliability of a component over time. This distribution has a particular shape that tends to zero, as you can see in the second equation of the diagram. So we can see that when x tends to zero, the um, the 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 equation tends to zero. Okay, while when x tends as a value over zero, the function has the shape of 1 minus e at minus lambda multiplied for x. Okay, so we are considering this particular type of function that is very used when we are dealing with the reliability of components. The point is, this is the context, but the point is that to represent, as we saw in the previous graph, to represent in this way this function that is again a cumulative distribution function, so uppercase f x of x is a CDF, we have to define the what? The probability density function. But this is just a little mathematical trick, but it's quite intuitive. If the cumulative distribution function is defined as an integral of the probability density function, of course, the probability density function is the derivative of the cumulative distribution function. Of course, we are always dealing with continuous random variable, okay? So if, let me take the whiteboard just to understand this very important concept, okay? If we are dealing with ex, uppercase x continuous, okay, we saw in the previous slide that f uppercase f of x, x of x, so the cumulative distribution function, is equal to minus the integral between minus infinite to x of what? F x x the x. Okay, we can use both u or x is just the same. Where f x of x, since we are in the concept of continuous random variable, is the probability density function. Okay, the point is that we have just to get the value of the probability density function, we have to derivate the cumulative density function. So fx of x is equal to what? Well, is equal to derivative of fx x divided by the x. It's just the inverse operation, okay? So the probability density function is the derivative of the cumulative distribution function. And that's the point when we are dealing with, again, continuous variable, random variable. Okay, just because we are discussing about the probability density function, just a brief recap I put here in brackets or something like this. If x is discrete, we don't discuss, we don't speak about probability density function, but we discuss about probability mass function. And the probability mass function is fx of x of what? Of the probability that x is equal to lowercase x. Okay? So we have both the solution in this white paper, in this whiteboard. Okay? So now let's come back to the slide. Now we have defined what is written down in slide 27. So we have defined the value of the probability density function f lowercase f x of x. Okay, how do we pass from this first equation, 1 minus e elevated to minus lambda x, to this one? Of course, by using the derivative function. Okay, I don't want to go into details at this moment. But the point is that now we can represent graphically the distribution. Okay. So let me come back to the whiteboard. And if we want to represent the solution, we can try to do it in this way. Okay, so we have our x-axis. Okay. We have fx of x. And in blue, I draw the exponential function. Okay. This is our exponential function. The exercise, the example, asks to calculate the probability that, of course, we are dealing with electronic component, but it doesn't matter, as a lifetime between 0 and 20 years. The point is that if we have drawn the function, the only stuff that the only thing that we can do is identify the 2 points that the exercise asks, so 10 and 20. We can draw a line, and then the probability that the components has um, a life between 10 to 20 years is this area. Okay? Because we are dealing with continuous random variable. So this is the probability of what is the probability that our random variable, it is a continuous random variable, is between 10 to and 20. Okay, this is a graphical solution of our problem. So in this slide, I think you have all the calculation of the solution. So of course, if for the properties that we saw before, so this one, the last one, the fourth probability, the fourth properties of the probability density function, we saw that the probability of x between A and B can be written down as the probability, the cumulative distribution function in B and minus the cumulative distribution function in A, that is the integral between A and B of the probability density function. So that's is what is done in this slide. So x is between 10 and 20. So we pass to the integral of what of our probability density function that, if we come back, is lambda exponential of minus lambda x. And so on, we can go on with the implementation, and we can find that again the solution is this one. So this one, the last row of slide 29. Okay, but the important thing is to understand from a graphical point of view, so what I've drawn here in the whiteboard, what's the meaning of the probability in the context of continuous random variable. So we can go on. And it is important to underline that in this context of probability density function, we are therefore again dealing with distribution. As already mentioned in the previous slide, of these distributions, we know that we have to find values that indicate their central tendency and dispersion. We have already mentioned this concept in the previous lesson, of course. For the position index, we need to find that. So just we are summarizing what we have already saw in the previous lesson. For the position index, we saw that we need to find a single value that represents a group of experimental results. So imagine you have conducted an experiment or collected data, okay? And now you have a whole set of numbers. But the point is, how can you describe this set of data succinctly, successfully? One approach is to find a single value that represents the average position of all these numbers, which, this is very important, which brings us to the idea of the expected value, or we can also say of central value of a distribution. So consider, if you will, several physical masses distributed along a line. To find a single point that represents the balance point or the center of mass of these distribution masses, of course, you will calculate their centroid. This is some way the analogy to how we determine the expected value of a statistical distribution. Because the expected value gives us a point of equilibrium. So a balance point of the distribution, which is, and since it is defined as a balance point, it is often referred as central value, okay? Statistically, the expected value of a random variable uppercase X is denoted as E of X. And it is calculated as the weighted average of all possible values that X can take, with the weights being the probability of this value. This calculation offers us a measure of the center of the distribution of the values. And this EX, as you can see from slide 31, but we will go into details later about this slide, is just to show you the symbol of the expected value, that is E of X. Sometimes it is also represented with the Greek letter mu that we have already seen in the previous lesson. Okay, mu of X. However, an important warning to remember is that the expected value will only accurately represent the central point for symmetrical distributions. Because in symmetric distribution, the mean, the median, and the mode all occur at the same point that are media. The mean, the median, and mode are different statistics to describe the distribution that we will see in the next lesson. And so it is important to understand that the expected value accurately represents the central point only for symmetrical distribution. So based on what we said, we can calculate the value of E of X. Again, and this is quite obvious, E of X has a different formula depending on whether we are dealing with discrete variables, so where the random variables can only take certain values, or continuous variable. In the slide 31, we can see the two formulae. The first one is for the discrete case. And we can see that in this case, E of X is equal to the sum of the xj multiplied by the probability of xj, okay? Because, again, as we already mentioned, the expected value is all the value that the variable x can assume multiplied by the weight of this value, and the weight is given by the probability. On the other hand, if we are dealing with, so just to be clear, the probability of xj is the probability of the mass function, okay, is the probability mass function fx of xj, but we will see later this concept. So the expected value for the discrete random variable is the sum up of the values assumed by the variable multiplied by their probability. So namely, the values assumed by fx of xj. And in the case of discrete variable, the expected value is a sort of weighted average. Let's pass to the continuous situation, because for the continuous variable, the expected value can be calculated, of course, by using what? The integral between minus infinity to plus infinity of x multiplied by the probability density function, fx of course, because we are dealing with the integral, the x. And at the bottom of the slide, we have what we have already mentioned. So if the expected value is calculated with theoretical values, it is indicated with the Greek letter mu. Whereas, so on the other hand, if it is calculated with experimental values, it is indicated with m. So just to be clear, I take the whiteboard. And again, we have the definition of expected value, but the definition of expected value is different if we are dealing with x discrete, or if we are dealing with x continuous. If we are dealing with x, so random variable, a discrete random variable, the expected value E of x is equal to the sum that goes from j equal to 1 to n, where n, uppercase n, is the number of mass points of the specific mass point xj multiplied by its probability. So probability of xj. But we know, again, for what we have already seen in the previous lesson, that the probability of xj is the probability mass function. So we can write also the expected value of a discrete random variable as follow: xj multiplied for fx of x. Of course, fx of x in the case of discrete random variable. So this is a probability mass function. So let me erase this part. On the other hand, if x is continuous, we have a different formula, because the expected value of x is equal to the integral between minus infinity to plus infinity of what? Of x multiplied by fx x dx. Okay, and in this case, the fx of x is the probability density function. Okay, so we are in these two different cases. Let me come back to the presentation. And here we have a different example for the calculation of the expected value. Of course, the case of discrete random variable, it's easier to understand. While for in the case of a continuous random variable, you have to remember something about the integral. Anyhow, we can start from the usual example of rolling of a six-sided die. And the slide tells us that we can consider a uniform discrete distribution. What does it mean? It means that the distribution, so the mass probability function, because we are in the discrete case, is uniform. It means that each mass point has the same probability, so has the same value of the mass distribution. Okay? So if we want to calculate the expected value, in this case, we can use the formula that we already saw before. So if we roll a six-sided die, we have, again, but we have already seen in the previous slide, that we know that if we roll a six-sided die that is fair, of course, because this is why we are considering a uniform distribution, we have six possible solutions. So because in the fair die we have six sides, okay? We have the side 1, the side 2, the side 3, the side 4, the side 5, and the side 6. Since the die is fair, the probability of each side is the same, that is 1/6. But by using the definition of expected value, we know that we have to sum, in the case of discrete random variable, we have to take the mass point and multiply it for its probability, so 1 multiplied by 1/6, and sum all the possible combinations, all the possible solutions. So here we can see that have the side 1 that is multiplied for its probability, that is 1/6. Then we have to sum the second side, that is a second possible solution, multiplied for its probability 1/6. And we can go on until the last side, that is 6, multiplied for its probability, that is again 1/6. And this is why we are considering a uniform discrete distribution, because all the sides has the same probability, that is 1/6. If we sum up all these things, we obtain 21/6, that is equal to 7/2. Okay? If you take a look to the results, it's quite strange, because we obtain 7/2. That is a decimal value, okay? It is, we can also consider that since we are dealing with positive non-decimal number, we can presume to have an integer number as a solution. However, it's important to understand that the expected value is a theoretical value. So it's not necessary that the expected value assume one of the mass point results. Okay, this is why it is a decimal value instead of an integer value. Of course, the reasoning that we have already do with the discrete random variable can be made also for the continuous distribution. Here at the bottom of the slide, we have an example of the results of an instrument that it produce because this instrument produce in an indifferent manner and it results in the range between 1 and 6. And this is the case of continuous distribution of uniport type. So we have all the possible results between 1 and 6. And since it is uniform, it has all the solution has the same probability that is 1 over 5. And so instead of using the sum, we can use the integral, and if we use the formula of the expected value for continuous variable, random variable, is the integral between minus infinity to plus infinity of x multiplied by the probability density function, fx of x. Okay, so since we are measuring in a range between 1 and 6, is the integral between 1 and 6 of what? Of x, and the probability density function, since we are dealing with a uniform, is 1 over 5. If we know the basis of integral calculation, we can find that the result is this one. And again, we find out that the expected value is 7 over 2. Just to be clear about this example. So let's come back to the example of in the discrete case that it's also easier to represent. We are dealing with the rolling of a fair die. We know that there are 6 possible solutions in this case. So X again is a discrete random variable that looks at the face that comes out from the rolling of a die. Okay? We know that if we roll a fair die, we can obtain 6 possible solutions. So 1, 2, 3, 4, 5, and 6. These are all the mass points. Okay, so mass points. So all the possible solution of our experiment. Okay. Now to calculate the expected value, we have to define the probability, so the mass distribution function, of each of these mass points. So we have to calculate the probability. Okay. For instance, for 1, we have to calculate the probability that x is equal to 1. But the probability that x is equal to 1, we can also write as fx of what? Of 1. Okay. But if we are dealing with a fair die, we know that this probability is equal to 1 over 6 because all the sides has the same probability to face up. Okay. So now of course, we have to do this calculation for all the mass points, but as we know, this experiment is described by uniform distribution, so each side has the same probability, it is 1 over 6. Now we can calculate the expected value because the expected value is equal to the sum over the xj of what? Xj of fx of xj. What does it mean? That we have to consider all the combinations. So if xj is equal to 1, we are dealing with the first side of the die. So 1, this is the phase 1 of the side of the die. That has a probability to phase up equal to 1 over 6. Then plus what? The second side of the die, that is equal to 2 second side multiplied by 1 over 6. Then the third side, that is 3 multiplied by 1 over 6 plus 4 multiplied by 1 over 6 plus 5 multiplied by 1 over 6 plus 6 multiplied by 1 over 6. And all this stuff is equal to 7 over 2. That again, as already mentioned, is a decimal value, but the point is that it's possible because the expected value is a theoretical value. Okay? Let's come back to the slide. In slide 33, we have another important concept that to verify if we do correctly our application of the formula, it says that we can also do a double check. So what does it mean? So we can check if the total probability of both the sample is equal to 1, because one of the properties that the total probability for both should be for both the unit for discrete and continuous cases should be equal to 1. Indeed, if, of course, we sum all the probability, we can see that in the case of the roll of a six-sided die is equal to 1 because it's 6, so the number of side, multiplied by the probability 1 over 6 that is equal for all the sides. And the same as for the results of an instrument. This is the slide 33 is only a double check if we did correctly in the previous slide, okay? Here is another example of the example that we have already used in the other lesson. So the sum of the results obtained rolling two-sided dice. Again, we are considering that the dice are fair. It's a bit more complicated because we have more possible solution. I just recall this graph that in which in the last row we have all the possible solution that goes from 2 to 12 because we are dealing with the sum of two six-sided dice. And over the last row, we have all the possible combination that we can have for the solution. For instance, we can have a sum of 7 of the two dice with the combination 6, 1, so 6 for the first die and 1 for the second one. 5 for the first one, 2 for the second one, and so on until first for the first one and 6 for the second die. Okay, just a recap of what we have already seen. So if we want to calculate the expected value of this problem, we have again, we are in the, of course, discrete random variable. We have to apply the formula of the expected value. That is the same of the previous example. But in this case, we have more possible solution because we have more mass points. So, but the the reasoning is always the same because we have to take the first mass point, that in this case is 2, and multiply the 2 by its probability. Which is its probability is 1 over 36, because to obtain the sum equal to 2, we have that the first die is equal to 1 and the second die is equal to 1. So we have only one possible combination. And the total number of combination is 36. So the probability to obtain the side 2 is equal to 1 over 36. So for the first mass point, we have the contribution of 2 multiplied by 1 over 36. And if we go on for all the possible solution, let me do the same for, I don't know, the mass point 9. For 9, we have, of course, the value of the mass points, so 9, multiplied for what? All the possible, the probability of obtaining 9. Since we have 4 possible combinations to obtain a sum equal to 9, that are 6 for the first die, 3 for the second die, 5 for the first die, 4 for the second die, or 4 for the first die, 5 for the second die, 3 for the first die, and 6 for the second die, we have 4 possible combinations over a 36 total combination, so the probability to obtain 9 is 4 over 36. If we sum all the contribution, we obtain that the expected value of this experiment is equal to 7. Okay? Let's go on with the other important index to describe the distribution. That is the dispersion index. We have already seen that for the dispersion, so we have already seen that for the dispersion of a distribution, we can use the variance that is indicated with sigma squared, and it is equal to the expected value of x, so the random variable, minus mu. But what is mu? Mu is the expected value of x, okay? So the variance, the sigma squared, is defined as the expected value of the square of the difference of uppercase x from its expected value mu. And in the case of discrete distribution, assume the following formula. Okay, is always a sum. While for this, sorry, there is a mistake. For continuous distribution, this is the solution. So the last case is for continuous distribution, not discrete distribution. Okay, so instead of using the sum, we use the integral. Okay. So let's see some example. An important thing to say is that just a curiosity is why we are using the square. Because if we do not consider the square of the expected value, we have a problem with the contribution. So we have that the positive contribution and the negative, there is a compensation between positive and negative contribution. So the value of the variance tends to 0. And so this is why we use the square in the case of variance. So again, here we have the example of sorry, here we have the example of the rolling of a six-sided die. Okay, here we have the formula, and again, if we use the formula described here for discrete distribution, we can solve the example. Let me open the whiteboard. So in this case, we can solve together. But of course, we will see also this concept in the during the exercise, so the practical lecture. Okay, so we are dealing with a discrete random variable. We want to calculate the variance. Okay, the formula for the variance of the discrete random variable sigma squared is equal to the expected value of x minus mu squared, that is equal to j from 1 to n of xj minus mu squared multiplied by the probability of xj, that is the probability mass function, fx of x, of course. So if we are dealing with the problem of the rolling of one side or one die, okay, again, we have six possible solutions. So we have six possible xj. We have to calculate, just to remember, this is the expected value of x, that in this case we saw that is equal to 7/2, so 3.5, okay? We know that we have six possible mass points, 1 to 6, and the probability is always 1/6. Okay, now we can calculate the variance, because the variance in this case is for 1, for the first side, is just 1 minus 7/2 up to the 2 multiplied for its probability, 1/6. Okay, and we can do the same for all the side of the die. So 2 minus 7/2 up to the power of 2 multiplied by 1/6 plus 3 minus 7, 2 multiply 1/6 plus 4 minus 7/2 up to 2 multiply 1/6 plus 5 minus 7/2 squared 1/6, and last but not least 6 minus 7/2 of squared 1/6. If we do the sum of all these things, we obtain the results, that is 7.5/6. Okay, this is how we use the variance formula. Let's come back to the slide. We have also the example of the sum of the results obtained rolling two sides dice. It's just the same. It's a bit longer, of course, because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possible solutions. But the reasoning is just the same that we have already seen. In slide 38, there is only a particular example that we want to cite in this this lesson. That is, if we are evaluating the variance of a continuous uniform distribution in the interval, in the symmetric interval, so interval that goes from minus a to plus a, the variance, so the sigma squared, is equal to, it's not necessary to calculate all the value of the variance, but we can remember that the variance is equal to x squared over 3. But it's just an example, it's just a curiosity. The last important thing for this lesson is that from an experimental point of view, so from an experimental point of view, we do not know the value of mu, and neither the value of sigma. So we have to estimate their value starting from the available experimental data. Actually, I don't want to go into details of the next slides because there is a lot of mathematical stuff. But the important thing you need to remember is that a corrected estimator of the mean. What does it mean, corrected estimator? Corrected estimator means that the expected value of the estimator gives us the result that we are estimating. Okay? So a corrected estimator for the mean, so for the for the mean of the distribution, for the central value of the distribution, is the arithmetic mean. It is indicated with the symbol mx. That is, of course, is a standard arithmetic. So if we have three numbers, we have to sum the three numbers and divide it by 3 because we have three numbers. So it's quite easy. So we have a sum of the value of xi divided by n. That is the number of data that we have. Okay? In the second row of this slide, so here in the second formula, we have just the definition of a corrected estimator. So if we calculate the expected value of the arithmetic mean, so mx, we obtain, by using the formula, we obtain that the expected value is equal to mu. So what we are estimating by using the arithmetic mean. Okay, this is why the max is a corrected estimate. On the other hand, for the variance, it's more difficult. Because at the first point, the first idea, we can try to consider mx instead of mu in the formula of the variance. However, if we consider mx instead of mu, there are a problem because the sum of the differences is identically 0. Okay, that's the problem of the sum of the positive and negative contribution that I have already mentioned before. So the point is that we cannot use the arithmetic mean in the formula of the variance. So here there are some mathematical formula that I don't want to go into detail, but the important thing is this one in slide 44. Okay, so I don't want that you remember the proof of why we are obtaining the last formula of slide 44. The important thing is that you remember that the corrected estimator of the variance is the so-called S squared, which has the following formula. Okay, that one, n over n minus 1 of the expected value of xi minus mx, so the arithmetic mean squared. Okay, this is the very important thing because we will use in the exercises this formula. Okay, so that's the important stuff. And indeed, this is the demonstration that S squared is a corrected estimator, because if we calculate the expected value of S squared, we obtain what? Sigma squared. So this demonstrates the fact that S squared is a correct estimate. Okay, I think that for today is enough. In the next lesson, we will pick up from this slide, so slide 46, in which we introduce the concept of discrete distribution. Okay, so thank you all for your attention and see you in the next lesson.